Today we're diving into one of the most powerful strategies in engineering, science, and entrepreneurship, the test at the edges strategy. This principle has saved countless projects from catastrophic failure and revealed breakthrough discoveries. So what exactly does testing at the edges mean? It's the practice of deliberately pushing systems to their extreme operating conditions early in development, rather than testing only under normal, comfortable conditions. We're talking about extreme temperatures, maximum loads, highest speeds, intense pressures, and noisy environments. These are the boundaries where systems reveal their true limitations. Here's a question. Why do normal conditions hide critical flaws? Because most systems are designed with some safety margin. Under typical use, these margins mask fundamental design weaknesses that only emerge at extremes. Picture this visualization. The green zone represents normal operating conditions where everything appears fine. But the red zones at the edges represent extreme conditions where hidden failures lurk. Most engineers never venture into these zones until it's too late. Let me give you a real-world example that demonstrates the catastrophic cost of not testing at the edges. The Space Shuttle Challenger disaster in 1986. The critical O-rings that sealed joints in the solid rocket boosters had never been tested below 53 degrees Fahrenheit. Engineers assumed they would work fine across all temperatures. On launch day, the temperature was 36 degrees Fahrenheit, well outside the tested range. The O-rings lost elasticity in the cold, failed to seal properly, and hot gas escaped. The launch temperature was 36 degrees, which was less than the minimum tested temperature of 53 degrees. This 17-degree difference was enough to change the material properties catastrophically. The result was the loss of 7 lives, billions of dollars in damage, and the shuttle program was delayed for years, all because the system wasn't tested at temperature edges. Let's dive into the physics of why materials fail at extremes. Understanding this will help you appreciate why edge testing is non-negotiable. The elastic modulus of materials typically follows an exponential decay with temperature. E of T equals E naught times e to the negative alpha times T minus T naught, where alpha is a material constant. For elastomers like O-rings, the elastic modulus can drop by 50% for every 30 degrees Celsius decrease in temperature. This means they become significantly less springy and responsive in cold conditions. If the modulus at 53 degrees Fahrenheit is 100 megapascals, then at 36 degrees it might drop to around 65 megapascals. That's a 35% reduction in stiffness. This reduction means the O-ring responds more slowly to pressure changes and may not compress fully into the groove, leaving gaps for hot gas to escape. Let me give you an analogy that makes this concept crystal clear. Imagine you're building a bridge designed to hold 100 cars. Here's a bridge with a normal load of 100 cars. Everything looks stable and safe. The bridge holds up perfectly under this expected load. Now here's a critical question. Would you test this bridge with only 50 cars and then declare it safe for 100 cars? Of course not. That would be engineering malpractice. Smart engineers test with 150 or even 200 cars. They want to know exactly where the breaking point is, what fails first, and how the system degrades beyond design limits. Here's the edge test with 200 cars. Notice the bridge is sagging more, stresses are visible, and we can identify which components are most stressed. This information is invaluable. Let's talk about the mathematics behind safety factors and why they're not enough without edge testing. The safety factor is defined as ultimate strength divided by design load. Engineers typically use safety factors between 1.5 and 10, depending on the application. For aerospace applications, safety factors are typically 1.5 to 2.0 because weight is critical and we need efficiency. For civil structures like bridges and buildings, safety factors are 3 to 5 because human safety is paramount and weight is less critical. But here's the critical issue. Safety factors assume we actually know the true failure mode. If we've never tested at the edges, we might not know what actually fails first. Consider this historical example. Before World War II, engineers didn't know about brittle fracture in steel. Liberty ships were breaking in half in cold North Atlantic waters because nobody had tested the steel at those temperatures. Let's examine the ductile to brittle transition in materials, a phenomenon only discovered through edge testing. Fracture toughness is given by KIC equals y sigma square root of pi a, where y is a geometry factor, sigma is applied stress, and a is crack length. For steel, the fracture toughness KIC drops dramatically below what's called the transition temperature. Above this temperature, steel is ductile and tough. Below it, steel becomes brittle and cracks propagate easily. The transition temperature for mild steel is approximately -20 to +20 degrees Celsius. This is exactly the range where those Liberty ships were operating. This graph shows how fracture toughness changes with temperature. At warm temperatures on the left, the material is ductile with high toughness. But as temperature drops past the transition point, toughness plummets, and the material becomes dangerously brittle. Now let's explore what happens when we test at load edges. This reveals stress concentrations that are invisible under normal loads. Maximum stress equals Kt times nominal stress, where Kt is the stress concentration factor. This factor depends on geometry. For a simple circular hole in a flat plate, the stress concentration factor is 3. This means stress at the hole edge is 3 times the average stress in the plate. But for a sharp notch or crack, the stress concentration factor can exceed 10. Tiny imperfections become catastrophic failure points under high load. If the nominal stress is 100 megapascals, the maximum stress at a crack tip could reach 1,000 megapascals. This is enough to exceed the yield strength of most structural materials. Under normal loads, you might have 30 megapascals nominal stress, giving 300 megapascals at the crack tip. This is still below yield strength, so everything seems fine. But edge testing at 100 megapascals nominal reveals that this crack will cause catastrophic failure. You've now identified a critical flaw that would have been a ticking time bomb. Now let's shift gears and talk about how the test at the edges strategy applies to entrepreneurship and business systems. You might ask, how does edge testing apply to startups and products? The principles are identical, just the variables change. Test your website or app with 100 times normal traffic early in development. Don't wait until you're on the front page of a major news site to discover your servers can't handle the load. Test your customer service systems with angry, unreasonable users before you have thousands of real customers. Edge cases and human behavior will reveal weaknesses in your processes. Test your product with users who have absolutely zero technical knowledge. If your grandmother can't figure it out, you have a design problem that will limit your market. Here's a visual representation. Your system works for normal users in the green box. But edge testing with angry users and clueless users in the red and orange boxes reveals breaking points and confusion that normal testing never would. One of the most exciting aspects of edge testing is the unexpected discoveries. Testing at extremes often reveals entirely new phenomena. Superconductivity was discovered by Heineke Kamerlingh Onnes in 1911 when he tested electrical resistance at 4 Kelvin, an extreme temperature edge. Nobody expected resistance to drop to exactly 0. Superfluidity in liquid helium was discovered by testing at extreme cold temperatures. Below 2.17 Kelvin, helium behaves in ways that defy classical physics, flowing without viscosity. Quantum tunneling was discovered by examining what happens at the edges of potential energy barriers. Classical physics said particles can't cross, but quantum mechanics revealed they can tunnel through. The tunneling probability is proportional to e to the -2 kappa L, where kappa equals the square root of 2 meters times v minus e over h bar squared. This only becomes significant at quantum edges. Let's talk about an often forgotten edge: noise testing. Environmental noise can destroy system performance in ways that surprise engineers. Electronic noise increases with the square root of temperature. This is Johnson-Nyquist thermal noise, and it sets fundamental limits on measurement precision. The noise voltage equals the square root of 4 times Boltzmann's constant times temperature times resistance times bandwidth. As temperature increases, noise increases. At room temperature, a 1 kilo ohm resistor has about 4 nanovolts per square root hertz of noise. This seems tiny, but for sensitive measurements, it's a critical limitation. In a 1 megahertz bandwidth, this becomes 4 microvolts of noise. If your signal is only 10 microvolts, your signal-to-noise ratio is terrible. Testing at high temperatures reveals this limitation early. At 100 degrees Celsius, noise is 1.12 times higher. At 200 degrees, it's 1.26 times higher. Your system that worked at 25 degrees fails at 150. Speed testing pushes systems to their bandwidth edges. This reveals timing issues, race conditions, and synchronization failures. For RC circuits, maximum frequency is 1/2 pi r circa. As you push frequency higher, the circuit response degrades predictably. But digital systems have non-obvious timing failures. Setup time violations, hold time violations, and metastability only appear when you push clock speeds to the edge. A processor that works perfectly at 1 GHz might fail unpredictably at 1.5 GHz. Not because of heating, but because of subtle timing issues in the longest signal paths. The timing constraint is setup time, plus propagation time must be less than clock period. As clock period shrinks with higher frequency, this constraint becomes harder to meet. Let's work through a detailed numerical example of edge testing on an airplane wing to see how the math works in practice. Suppose we're designing a wing that must support a 2 grams load factor during normal maneuvers. This means twice the aircraft weight. If the aircraft weighs 50,000 kilograms, the design force is 2 times 50,000 times 9.8, which equals 980 kilonewtons. But aviation certification standards require demonstrating the wing can withstand 3 grams before the first flight. This is edge testing mandated by regulation. The test force is 3 times 50,000 times 9.8, which equals 1470 kilonewtons. This is 50% higher than the design load. Wing bending stress scales linearly with load. If the wing experiences 200 megapascals at 2 grams, it will see 300 megapascals at 3 grams. Test stress equals 3/2 times 200, which is 300 megapascals. For aluminum 7075 T6, the yield strength is about 500 megapascals, so we're at 60% of yield. This test reveals if any fasteners, ribs, or skin panels are undersized. Under 2 grams, everything might look fine. But at 3 grams, a weak fastener might start to yield or crack. Despite all these benefits, many engineers and entrepreneurs avoid edge testing. Let's understand why and address these concerns. Reason 1 is fear of finding problems late in development. If you've invested months building something, you don't want to discover it fails at the edges. But finding problems during testing is infinitely better than finding them in production when real users or real systems are affected. Edge testing early is a form of insurance. Reason 2 is that edge testing requires expensive equipment and takes time. Testing to 200 degrees requires thermal chambers. Testing to 10 grams requires centrifuges. But consider this. Failures in the field are typically 100 times more expensive than testing costs. A single recall can bankrupt a company. Testing is cheap insurance. Reason 3 is the belief that computer simulations make physical testing unnecessary. Modern finite element analysis is incredibly powerful. But here's the problem. Simulations only reveal what we explicitly model. They can't predict unknown failure modes or material behaviors we haven't characterized. Let me give you a practical strategy for implementing edge testing in your projects, whether they're engineering systems or business ventures. Step 1. List every operating parameter in your system. Temperature, pressure, voltage, speed, load, noise, number of users, data throughput, whatever applies to your domain. Step 2. For each parameter, define both the expected normal range and an edge range that's at least twice as extreme. If you expect 0 to 50 degrees, test -20 to 100 degrees. Step 3. Create a test matrix that hits multiple edges simultaneously. Real-world failures often occur when 2 or 3 parameters are at extremes together. Here's a simple test matrix. Test 1 uses cold temperature and normal load. Test 2 uses hot temperature and maximum load. This combination testing reveals interaction effects. Step 4. Test edges early in development, before full system integration. Test individual components at temperature extremes before assembling the complete system. Step 5. Document all edge behaviors, even when components pass. Knowing that your sensor works, but with reduced accuracy at -40 degrees, is valuable information for system design. Let's talk about return on investment for edge testing, because this is what convinces managers and executives to allocate resources. Return on investment equals the cost of failure prevented minus cost of testing, all divided by cost of testing. Consider a new smartphone design. Edge testing might cost $500,000 for environmental chambers, drop testing, and extreme usage scenarios. The cost of comprehensive edge testing is $500,000. This seems expensive for a startup. But the cost of a single recall for overheating batteries is at minimum $50 million. This includes replacement costs, shipping, labor, and brand damage. The ROI is 50 million minus 500,000 divided by 500,000, which equals 99. That's a 99-to-1 return on investment, or 900% return. Even if edge testing only has a 1% chance of catching a critical flaw, the expected value is still $500,000, which equals the testing cost. Anything above 1% is profit. Let's examine another historical case where lack of edge testing led to tragedy: the Ford Pinto fuel tank fires in the 1970s. The Pinto was tested at normal collision speeds of 25 to 35 miles per hour. At these speeds, the fuel tank performed adequately. But rear-end collisions at 40 miles per hour or higher caused the fuel tank to rupture and ignite. The bolt from the differential would puncture the tank. Kinetic energy equals 1/2 m versus squared. Energy scales with velocity squared, so a 40-mile-per-hour collision has twice the energy of a 28-mile-per-hour collision. The result was 180 deaths, lawsuits exceeding $500 million, and immeasurable damage to Ford's brand reputation, all preventable with proper edge testing. Now let's apply edge testing principles specifically to software engineering, where the edges are different but equally critical. Test your application with 1 million concurrent users, not just 1,000. Use load testing tools to simulate this traffic before your viral moment happens. Test with malformed input data. Try negative numbers where you expect positive. Use special characters. Test SQL injection attacks. Edge cases in input data reveal security vulnerabilities. Test with both 0 network latency and with 10-second latency. Real users experience everything from fiber connections to terrible mobile networks. Set your timeout values at expected latency plus 3 standard deviations. This captures 99.7% of normal variation while still catching true failures. There's a significant psychological barrier that prevents people from edge testing. Let's address this head-on. We have a cognitive bias toward assuming normal conditions are representative of all conditions. This is called the availability heuristic. We remember typical experiences more than rare extremes. But in engineering and business, it's the rare extremes that often determine ultimate success or failure. A system that works 99% of the time, but fails catastrophically, the other 1% is unacceptable. Overcoming this bias requires deliberate practice and systematic checklists. Make edge testing a mandatory step that can't be skipped, like pre-flight checks for pilots. Let me introduce an advanced concept that explains why edge testing at extremes reveals both infant mortality and wear-out failures. The failure rate lambda as a function of time equals lambda naught plus alpha times t to the beta, where lambda naught is the infant mortality rate and alpha t to the beta represents wear-out. Early failures, called infant mortality, occur due to manufacturing defects, contamination, or assembly errors. Edge testing stresses these weak points and makes them fail quickly. Late failures occur due to cumulative damage, fatigue, and wear. Edge testing accelerates this process, letting you see 10 years of wear in 1,000 hours of testing. This is the famous bathtub curve. Failure rate is high initially due to defects, drops to a constant low rate during useful life, then increases again due to wear out. Edge testing reveals both ends of this curve. You might ask, how do we accelerate time in testing? We can't literally make time move faster, but we can accelerate the physical processes. The acceleration factor equals e to the EA over k times the quantity 1 over t used minus 1 over t test, where EA is activation energy and k is Boltzmann's constant. For electronics, testing at 125 degrees Celsius instead of 55 degrees typically gives a 10x acceleration factor. 1 month of testing equals 10 months of field use. Let me summarize the key principles we've covered about test at the edges strategy. First principle: normal operating conditions hide critical design flaws that only reveal themselves at extremes of temperature, load, speed, or other parameters. Second, edge testing not only reveals known failure modes but often uncovers entirely unexpected phenomena and new physics. Third, The cost of comprehensive edge testing is trivial compared to the catastrophic costs of field failures, recalls, and loss of reputation. Fourth, these principles apply universally to hardware systems, software applications, and even business processes and customer service. Fifth, edge testing must be integrated early in the development process as a mandatory checkpoint, not treated as an optional afterthought. Let me leave you with a final thought. Edge testing isn't just about avoiding failures. It's also about scientific exploration and discovery. The edges of operating space are where nature reveals her deepest secrets. Superconductivity, superfluidity, quantum effects, phase transitions, all discovered at the edges. Every edge test you perform is an experiment that might teach you something new about your system, your materials, or even fundamental physics. The best engineers and scientists are deeply curious about what breaks and why. They don't fear edge testing. They embrace it as an opportunity for learning and innovation.